Hi everyone, this is Dr. Swaminathan SM, Associate Professor EC Department, SNS College of Technology. So now we will have the presentation like PI compensation. So already last class we discussed about the P compensation and its types and the disadvantages, advantages of the different compensation techniques. So here P controller with the example root locus method steady state error. How can you find the phase margin, gain margin following with the activity PI controller and the advantages, disadvantages of the PI controllers and the examples, the response of the system and summary. So P controller, that example means the P controller with a unique examples. With these examples, readers' knowledge about the stability and steady state error will also enhance. Consider the feedback control system which is shown in figure. So here this R of S is the input, summation is the summing point plus, that is plus minus, K is the constant term, and the transfer function that of the planned 1 divided by S into S plus 1 into S plus 2, and C of S is the output. So the root locus method, K is a proportional constant. It is also called error amplifier. The characteristic equation which is given. So based on the Routh-Hurwitz characteristic equation, K is the constant between 0 to 6. If K greater than 6 means it is unstable, equal to 0 means that is marginally stable. So based on this given root locus techniques, and the root locus techniques, its roots means that is equal to 0. So in characteristic equation, so K is equal to 0.2, 1, 5.8, etc. So to analyze the each value and shown the result, high value of the K, that examples K is equal to 5.8, it reduces the stability and reduces the steady state error. That is very important. So KPVA, KP means position velocity static error, and KV means velocity steady state error, Ka means acceleration steady state error. So it is defined 1 divided by 1 plus Kp, 1 divided by Kv, 1 divided by Ka. So it can be observed that K is values of Kp, Kv, Ka are the steady state error will shown in figure. Now we'll explain the result. At K is equal to 0.2, you can just substitute the value. So you can get minus 2.088. It is far away from the imaginary axis, so you can easily ignore it. So based on this, you can get the different root locus techniques. For the gain margin, so G of S into H of S equal to 0.2 divided by S into S plus 1, S plus 2. So in the present case, gain margin is 29.5 dB, phase margin is 81.5 degree. So based on the gain margin and phase margin, you can get another value, that is K is equal to 1. You can get the different value. So you can get minus 2.3247. You can easily remove it because it is minus far away from the particular value. So the G of S into H of S, that is equal to 1 divided by S into S plus 1, S plus 2. At K is equal to 5.8, that is very close to 6, and understand the system is stable. So most of it's complete in the border side. So this is called K is equal to 5.8. So in the present case of the open loop transfer function, 5.8 divided by S into S plus 1, S plus 2, the gain margin is 0.294 dB and phase margin is 0.919 degree. So it can be analyzed as compared as previous cases. It reduced drastically. So following with the activity, we will discuss about the proportional and integrated controller. So proportional and integrated controller means both are complete together. So proportional also come, integration also come. So proportional means that is in A of t is proportional with the integral part of 0 to t E of t plus A of t is proportional to E of t. So first one is the integral part, another one is the proportional part. So removing the sign of the proportional, you can get the Ki integral part of 0 of t into E of t plus Kp E of t. So Kp and Ki are called the integral and proportional constants. So the advantages, we are adding one pole at origin and one pole 0 somewhere away from the origin. As the pole is origin, its effect will be more. Hence, PI controllers will reduce the stability. So it reduces the steady state error drastically. Due to this function, is one of the most widely used controllers. Example, you can see R of S is the input, summation is the summing point, Ki is the constant, 1 by S is the value feedback system. Next is summation point and the transfer function. It is a closed loop control with the PI controller. So for the given schematic diagram, the value of K 5.8, Ki is the 0.2, it's the response, and K is equal to 5.8 you can get. So integral part reduces the stability, which does not mean the system will always stable. So in the present case we can add the integral part and the system becomes unstable. So this is the response of the system. So for the time response analysis, the x-axis is the time, y-axis is the amplitude. So here the time responses based on the figure, K is equal to 5.8 and Ka is the 0.2 value. So thank you. These are all called PI controllers. Thank you.